something impossible just happened. As the interstellar visitor 3I-ATLAS made its closest approach to our Sun, it did something that has scientists completely baffled. It accelerated, dramatically. Not the gradual speed increase you'd expect from gravitational forces, not the subtle push from solar radiation pressure. This was different, this was explosive, and then it turned blue. Bluer than the Sun itself. Let me say that again. An ancient comet that's been frozen in interstellar space for potentially billions of years suddenly started glowing with a color temperature hotter than our star's surface. That shouldn't be possible. If you want to understand what's really happening with the most mysterious object to enter our solar system since Oumuamua, hit that like button right now. Because what I'm about to show you will challenge everything you thought you knew about interstellar visitors. Let's start with the facts, because they're stunning enough on their own. Astronomers Chi-Sheng Lin from Lulin Observatory in Taiwan and Carl Battams from the US Naval Research Laboratory have been tracking 3I-ATLAS intensively for months. What they documented in the final days before perihelion has the scientific community scrambling for explanations. The comet's brightness didn't just increase gradually as it approached the Sun, it exploded in intensity at twice the rate it had been brightening before, twice as fast. In the 2 weeks leading up to perihelion, 3I-ATLAS was losing approximately 5.7 times 10 to the 28th power water molecules per second. That's 40 times more water vapor than it was releasing just 1 month earlier. 40 times more. One scientist described it as a fire hose on full blast. But that doesn't even capture the scale. This is more like turning on every fire hydrant in a major city simultaneously. Before we go further, make sure you're subscribed and notifications are on, because what's happening with this object is developing in real time, and you won't want to miss what comes next. But here's where it gets truly bizarre. The spectrum analysis revealed something that's keeping astronomers awake at night. The comet's light became bluer than the Sun's own spectrum. Think about what that means for a moment. The Sun's surface temperature is about 5,800 degrees Kelvin. That temperature produces the yellowish-white light we see every day. For 3I-ATLAS to appear bluer than the Sun, its emission source would need to be hotter, significantly hotter. We're talking about temperatures that simply don't occur on natural comet surfaces, even at close approach to a star. The blue shift indicates the presence of specific carbon molecules, C2 and amidogen compounds. These are signatures of active ice sublimation, yes, but the intensity and color temperature don't match any model of passive solar heating. This isn't a comet getting warmed up by sunlight. This is something generating its own heat at temperatures that defy comfortable explanation. Now, you might think this is just normal comet behavior taken to an extreme. Comets heat up near the Sun, ice turns to gas, they get brighter. Standard physics, right? Except 3I-ATLAS isn't following standard physics. The rate of change is wrong, the timing is wrong, the color temperature is wrong, and what we're seeing doesn't match what we know about comets from our own solar system, or even Borisov, the other well-studied interstellar comet. Space-based telescopes, SOHO, Stereo A, and the new GOES-19 satellite, all equipped with coronagraphs that can observe objects close to the Sun, captured images during this critical period. And what they saw has researchers deeply puzzled. The comet appeared as a faint but noticeably elongated spot, but here's what's strange. It had no visible dust tail. None. Just this stretched-out blue glow without the characteristic dust trail that comets normally produce. Every comet we've ever studied produces dust. It's what makes their tails so spectacular. Sunlight reflecting off countless particles of debris being blown away from the nucleus. So, where's the dust from 3I-ATLAS? Drop a comment below with your thoughts, because what we're looking at here doesn't fit into our comfortable categories. Some scientists have proposed an explanation that sounds reasonable on the surface. They suggest that initially, carbon dioxide gas was escaping from the comet at a distance of about 3 astronomical units from the Sun. This CO2 would have been cooling the surface of the nucleus, essentially acting as a protective layer that prevented water from sublimating. It's like a refrigerant layer, keeping the deeper ice frozen despite increasing solar radiation. But then something changed. That protective layer depleted, and when it did, the water ice underneath was suddenly exposed to direct, intense solar radiation. The result? An explosive increase in brightness and activity as billions of tons of water ice suddenly began sublimating all at once. That's the conventional explanation. And it's plausible. But there's a problem. It doesn't explain the blue color. It doesn't explain the acceleration. And it doesn't explain why the timing was so precise, as if a switch was flipped exactly at perihelion. There's another possibility, and this is where things get uncomfortable for some researchers. The composition of 3I-ATLAS's nucleus might be fundamentally different from anything we've seen before. Remember, this object didn't form in our solar system. It formed around a different star, in a different stellar environment, with different chemical conditions, possibly billions of years ago. What if its internal structure is nothing like the comets we're familiar with? What if there's something inside that nucleus? Some process, some material, some mechanism that we don't understand yet. The James Webb Space Telescope observed 3I-ATLAS back in August, before the perihelion passage. What it found adds another layer to this mystery. Webb's near-infrared spectrograph revealed that this comet has been transformed by billions of years of cosmic ray bombardment. We're talking about galactic cosmic rays, high-energy particles that permeate interstellar space, striking the comet's surface continuously for eons. According to research led by Romain Maggiolo from the Royal Belgian Institute for Space Astronomy, these cosmic rays have fundamentally altered the physical and chemical structure of 3I-ATLAS. Computer simulations suggest that cosmic rays have penetrated approximately 50 to 65 feet deep into the comet's surface, creating what scientists are calling a deep, irradiated crust. Here's what that means. This crust no longer resembles the pristine material from the comet's home star system. It's been cooked by radiation for so long that it's become something else entirely. The outer layers are now a shell of radiation-processed material, harder, denser, chemically transformed from whatever it was originally. But here's the critical question that nobody can answer. What's underneath that crust? If the explosive brightening and blue glow are coming from material that's been exposed by solar erosion of that protective crust, then we might be seeing the comet's original composition for the first time. Material that formed around another star, chemistry from a different stellar environment, compounds that don't exist naturally in our solar system. Maggiolo said something that should make us all pause. He said that 3I-ATLAS is now a product of its interstellar journey, rather than where it came from, at least on the outside. But what if the journey created something even more unusual? What if billions of years of cosmic ray bombardment didn't just alter the surface chemistry? What if it created something entirely new? Let's talk about the acceleration, because this is where conventional explanations really start to break down. When comets approach the Sun, they do experience non-gravitational forces. As ice sublimates and gas jets away from the surface, it creates thrust, like a natural rocket engine. We've seen this countless times with solar system comets. It's well understood, it's predictable, but the acceleration of 3I-ATLAS is different. The rate is too high, the timing is too precise, and the directionality suggests something more organized than random outgassing from a tumbling, irregular nucleus. Multiple research teams have noted that the acceleration pattern doesn't match standard comet models. Some have quietly suggested, in technical papers with carefully worded language, that the thrust-to-mass ratio observed would require either an extremely low-density object or a very efficient outgassing mechanism. Translation: either this thing is mostly hollow or something is generating thrust in a way that's far more efficient than passive ice sublimation. And then there's the colour. I keep coming back to this because it's the detail that bothers physicists the most. For 3I-ATLAS to glow blue, actually blue, not just blue shifted in spectrum, but visually appearing bluer than the Sun, requires a heat source. Natural fluorescence from gas molecules can produce colours, yes. We see green glows from carbon compounds, blue-green from cyanide. That's normal comet chemistry. But this is different. The intensity is too high, the colour temperature is too extreme. It's as if something inside the comet is burning. Not chemically burning, there's no oxygen in space for combustion, but generating heat through some process that produces temperatures far exceeding what solar heating alone can provide. One researcher, speaking on condition of anonymity, described it as thermodynamically problematic. That's scientist speak for "this shouldn't be happening." If you're finding this as unsettling as the research community is, share this video, because this story isn't getting the mainstream attention it deserves. Let me show you why the timing matters so much. When 3I-ATLAS reached perihelion, its closest point to the Sun, it was being hammered by approximately 770 watts of solar energy per square foot. That's intense. That's enough to vaporize water ice, to sublimate frozen carbon dioxide, to heat rock until it glows. But here's the thing. The explosive brightening and the blue glow didn't happen gradually as the comet approached perihelion. They happened suddenly, right at closest approach. Natural heating is gradual. As you get closer to a heat source, temperature rises smoothly. The response curve should be predictable. What 3I-ATLAS did was more like a threshold effect, like something activated at a specific temperature or a specific distance from the Sun. Some observers have noted, cautiously in forums and informal discussions rather than official papers, that this looks like a system that was dormant until it reached a trigger condition. Then it switched on. Now, I know what you're thinking. Couldn't this just be a threshold in the sublimation of some exotic ice? Some compound that remains stable until it hits a specific temperature, then sublimes explosively? Absolutely. That's possible. That's the explanation most scientists are hoping is correct. But what compound? What chemistry produces these exact characteristics? Research teams have run simulations using every known ice compound, every exotic molecular combination that could plausibly exist in a comet. Nothing quite fits. The blue color requires high temperature emission. The acceleration requires sustained directional thrust. The dust-free tail requires a composition that's almost purely volatile, with minimal solid material. Each piece individually could be explained by exotic but natural chemistry. But all of them together? The cumulative probability starts to approach implausibility. Let's talk about what happened during perihelion, because this is where the story gets really interesting. From Earth's perspective, 3I-ATLAS was directly behind the Sun during its closest approach. Complete observational blackout. We couldn't see what happened during those critical hours. But here's what we know. The comet went in showing unusual but explainable behavior. It came out glowing blue and accelerating. Something changed during that passage. Something happened when we couldn't watch. Amateur astronomer Worashate Boonplod from Thailand reviewed footage from the Goose 19 weather satellite and spotted what appeared to be 3I-ATLAS moving through the Sun's corona. If verified, and NASA hasn't confirmed this yet, it would be the first coronagraph image of an interstellar object during perihelion. But, more importantly, it might show us what happened during those blind hours. Multiple spacecraft are now positioned to gather more data. ESA's Hera and NASA's Europa Clipper both had trajectories that potentially intersected with 3I-ATLAS's ion tail. If either spacecraft sampled that tail, if they detected the composition of the material being ejected, we might finally understand what's generating the blue glow. Are the ions consistent with normal cometary ice, or is there something unusual, elements or isotopes or compounds that don't match anything in our solar system? ESA's JUICE spacecraft will observe 3I-ATLAS through late November, but the data won't be transmitted back to Earth until early next year due to communication constraints. So we're in a waiting period. Data is being collected, but we won't see the results for months. Here's what we're watching for as the comet moves away from the Sun. First, does the blue glow persist? If it fades quickly as the comet moves away from perihelion, that suggests solar heating was the primary driver. If it continues, if the comet stays unnaturally bright and blue, even as it cools, that suggests an internal energy source. Second, does the acceleration continue? Comets typically slow their non-gravitational acceleration as they move away from the Sun and outgassing decreases. If 3I-ATLAS maintains thrust, that's significant. Third, fragmentation. Did the intense heating at perihelion break it apart? If we see multiple fragments, that tells us about structural integrity. If it remained intact, that's informative too. Fourth, the dust. If 3I-ATLAS starts producing a normal dust tail as it cools, that suggests the unusual behavior was temperature-related. If it remains dust-free, that tells us something fundamental about its composition. The comet will be visible again from Earth in mid-November, emerging from the solar glare. Professional observatories are preparing comprehensive observation campaigns. Professor Avi Loeb has been vocal about the need for thorough investigation of 3I-ATLAS. He's not claiming it's artificial, let me be clear about that. He's saying that the unusual characteristics warrant serious scientific attention and that we shouldn't dismiss anomalies just because they make us uncomfortable. Loeb has requested that NASA release high-resolution images of 3I-ATLAS taken by the HiRISE camera on the Mars Reconnaissance Orbiter when the comet passed near Mars. Those images, if they exist, could show surface details that would help us understand what this object really is. So far, NASA hasn't confirmed whether those images were taken or why they haven't been released, if they do exist. Let's address the obvious question that everyone's thinking, but most scientists won't ask out loud. Could 3I-ATLAS be something other than a natural comet? The honest answer is, we don't have enough data to rule anything out definitively. The characteristics we're observing, the blue glow, the explosive acceleration, the dust-free tail, the precise timing, are consistent with exotic but natural chemistry. They're also consistent with other possibilities that make researchers uncomfortable to discuss. If you were designing a probe to survive billions of years traveling through interstellar space, you'd need protection from cosmic radiation, like a thick outer crust of processed material. A dormant power source that activates near stars, providing energy for observation or course correction, minimal dust production to reduce debris that could damage sensitive instruments, a means of acceleration for trajectory adjustments. I'm not saying that's what 3I-ATLAS is. I'm saying the characteristics we've observed happen to align with what you'd expect from such a design. That doesn't prove anything. It means we should gather more data before drawing conclusions. Here's what makes this moment so significant. For the first time in human history, we have the technology to study interstellar objects in detail, to analyze their composition, track their movements, measure their properties. 3I-ATLAS is only the third confirmed interstellar visitor we've detected. Each one has surprised us. Oumuamua accelerated in ways that couldn't be explained by standard outgassing. Borisov was relatively normal, but revealed chemistry from a different stellar environment. Now 3I-ATLAS is glowing blue, accelerating dramatically and challenging our models of how these objects should behave. Maybe all three are just natural objects with unusual properties. Maybe the universe is more diverse than our limited experience has shown us. That's the simplest explanation, and it's probably correct. But the blue glow keeps nagging at researchers. The acceleration pattern doesn't quite fit. The timing seems too precise. And when multiple anomalies appear in the same object, at some point you have to ask, are we missing something fundamental about what's possible? The next few weeks will be critical. As 3I-ATLAS moves through its post-perihelion phase, as our instruments collect more data, as the spacecraft analyze samples from its tail, we'll get answers. Maybe those answers will reveal exotic natural chemistry that expands our understanding of how matter behaves in interstellar space. Maybe they'll show us that we've been thinking too narrowly about what interstellar objects can be. Or maybe, just maybe, they'll force us to ask questions we never thought we'd have to answer. What is certain is that 3I-ATLAS has our attention. The scientific community is watching closely. Data is being collected from multiple sources, and whatever we discover will change something about how we understand these mysterious visitors from between the stars. This object has been traveling for potentially billions of years. It survived conditions we can barely imagine, and now it's putting on a show, glowing blue, accelerating dramatically, behaving in ways that defy easy explanation. The universe is speaking to us through this visitor. The question is, what is it trying to tell us? If you found this breakdown compelling, smash that like button and subscribe for updates as this story develops. Drop your thoughts in the comments. What do you think is causing the blue glow? Natural chemistry or something more? Share this video with someone who's as fascinated by cosmic mysteries as you are. This is the kind of discovery that reminds us why we study the cosmos, why we point our instruments at the darkness and ask, what else is out there? 3I-ATLAS is showing us something we've never seen before. Whether it's revealing new physics, new chemistry, or something even more profound, we're about to find out. Thanks for watching, and I'll see you in the next one.